I'm Christopher Diggins. I operate a small company, which is just me, myself, and my dog, called Ara3d, based in Montreal. I've been programming computers for a very long time. It's kind of like a hobby and a passion of mine. And I can occasionally get carried away with technical details and some things I might take for granted. So I really ask that, this presentation today is for you folks. And so I want you to stop me, ask questions. Uh, there is, don't worry about taking things off the rails. Like we can table things if we need to. And my goal today is to help you enjoy programming and become more effective at it, especially with regards to geometry. And so when I started to design this class, I started thinking to myself, well, about how 3D math is kind of hard, and it doesn't really need to be as hard as that. I spent many years trying to master it, so to speak, and I realized the trick is first off, understanding what everybody's talking about. I mentioned terminology, and that's a big problem because depending on your background, if you're in games or if you're used to software package A or software package B, you're gonna have a different jargon, different terminology for thing. A lot of people think that in 3D math, you have to remember formulas. And one of the great things about programming is we don't have to remember formulas at all. You write them down, put them in a function, and then you can forget about them, especially if your function's nicely named. And you're going to see that this is a common theme throughout. And this is actually a best practice for programming and a way to become more effective. The other thing is that numbers can mean different things, and it's very contextual. If I just say, well, I have the number 3.0 and it's a double, and my double X is 3.0, or my float X is 3.0, or my variable. The question is, what does this 3.0 really mean? Is it a angle? Is it radians? Is it a length? And the problem we have often is that we could actually be using data types to represent these things. Similarly for a vector 3, when we say I have a vector 3, all I know when you say you've got a vector 3 and I read your code is that you have 3 numbers. You have a tuple of 3 numbers. But is it a normal? Is it a vector? Is it a position? These are very distinct things. And the set of operations that you could perform on them is different. Other things that make it hard is, what is a quaternion? After all of this time, I couldn't explain it properly to you. And you don't need to know it. We need to understand what the operations are that you can perform on it, how it relates to other things, and then we can forget about it. The other thing that makes it hard is you have to understand what coordinate space things are in. 3D things are relative. And so you have to understand that there is no absolutes. You're always talking about a coordinate system relative to another. Other things that get tricky and that will really trip you up is the different conventions we have for representing things. Is Y up, is Z up, is the winding order of your triangles clockwise, counterclockwise, how are your matrices? These things make it hard. And that's one of the challenges we're going to have when you go from package to package. And I'll show you how we kind of tackled that in Plato.geometry. So how do you make it easy? Use lots of functions, keep your data types immutable, which means read only. Always compute things. So if you have you have functions that allow you to generate new things, think of vectors as if they're numbers, not just data types that you can change. And don't try to learn everything. You don't want to be an expert in, in order to, let's say, extract the translation of an affine matrix 4x4, it's the 4th column. You don't need to know all the details. You just need to know how to package them up in code that is easy. A lot of people get caught up on performance first, though. And you have to realize that most performance problems are actually due to bad logic at a high level. And they're usually hidden in plain sight because the code is too complex. So a lot of people don't realize that you should always be striving towards the simplest thing that could possibly work and do that first. All right, let's start diving into a little bit about, before I can even talk about geometry, I have to talk to you about graphics. Now, this dog, just because it was suggested by PowerPoint, and I just loved him. He's very cute. The point here is that graphics and geometry are two individual separate things, but unfortunately in the world programming, we're usually manipulating geometry so that we can ultimately render it on the screen using GPUs on graphics hardware. So they dictate the form of graphics APIs, of the programming interfaces. They dictate the functions we have, they dictate the data structures we use. So you have the graphics hardware dictates the forms of the APIs, and that dictates a lot of conventions that have existed and have been built up. What you need to know about a GPU is simply that it's massively parallel. It's really good at computing things on large arrays of data with floating point numbers very quickly. And this is very relevant to graphics. And for example, you might want to interpolate the normal vectors across a surface. So interpolating means, well, I've got one normal vector at one part of my triangle, another at another part of my triangle, another here. And so it's a curved surface. And so depending on where I am on the surface, I'm gonna have a slightly different normal. And GPUs are really good at computing that. GPUs can also project a point in 3D space using a projection matrix to a flat screen representation. Earlier, I talked about jargon. And if you read this paragraph, the vertex shader is this is a definition from the OpenGL wiki about what is a vertex shader. It says, it is the programmable shader stage in the rendering pipeline that handles the processing of individual vertices. Vertex shaders are fed blah, 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 blah. This is Greek. And then there's nobody in their right mind can actually understand this. And I wanted to say, look, just because people are bad at explaining things doesn't mean it's necessarily that complicated. You just have to find better ways of expressing things and keep asking, what do you mean? What does that word mean? What does this word mean? I'm going to give you a very simplified model of how graphics APIs work. And this is very important. Coming up with a simplified model of how a computer works is as good as understanding it for the purpose of programming. The details of how it works under the hood and in the hardware, on the silicon, is too complicated for most humans. But with a good model, you can actually accomplish lots of things. So triangles go into a memory buffer, and that memory buffer is transferred from your computer, from your CPU to your GPU. It goes through some processing. Then a vertex shader, which is written by a programmer in a programming language, a shader language like GLSL, computes the positions of the vertices and of the normals so that they're in world space. Then more processing happens. It's broken up into fragments or literal pixels. It's used to be sometimes called a pixel shader. And so for each visible pixel, what it does is it computes the color that is going to be rendered to the screen. This is basically what rendering is. So this is how this is basically the difference between vertex and fragment shaders. The vertex shader processes each vertex, transforms them, and as input, it gets vertex attribute data. So for every vertex, every point in space, you have to have associated data. So we call it a vertex because you have a position, a normal. It's necessary if you want it to look realistically lit. Optionally color UVs, and it outputs the transformed positions and the varying variables like the new normals. The fragment shader on the other side processes each fragment, determines the color by computing how is light interacting with the material at this particular spot on the surface. So it has an interpolated normal. It says, well, this surface has this normal, so light is reflecting off the surface at this angle, and it looks at the material properties, which are stored separately. And then from there, it can figure out a final color. And the different mechanisms it uses, the different algorithms, are called the shading model. So fragment shaders, again, they're written in shader code. I think it might be kind of fun just to show you something that we're not necessarily going to spend any time on because it's less about geometry, it's more about the graphics side. But I've talked to people about this topic before, and they said, well, this is kind of a black box for them. And it was for me for many, many years. Um, and this tool called Shader Toy exists that makes it easier for us to start to understand. Whoops. Hold on a second. Oh, yeah. Apologies. It makes it easier to understand what is going on. So this is just an example. You're probably seeing this at 1 frame per second. What I'm going to do is type this into the chat so you folks can all look at it at home and start to play with it. But what it is, it's a real-time tool that allows you to create graphics and manipulate shader code with instructions. There's lots and lots of fun examples. I'm going to put this into the chat for you folks. And what this is doing, this is actually the color pixel shader. This is the fragment shaders. And so you can write your own using this. And this is kind of like a C-type language, but it's called GLSL. All right. And that's enough of that. So. Oh, good. So I'm going to talk a little bit about software engineering. I got a few slides about that. And the reason why is I want for you to understand how you can start to make coding easier and have principles you can apply. This was something that was missing for me when I was learning to code, because it was like back in the day, it used to be just books about how not to code, like don't code like this and don't make that mistake and don't do this. But I was trying to understand, well, what are the principles I can follow to make it easier? And over time, I started to realize that actually the problem is people, we make things complicated. Programs, you know, when you start, they can be as simple or as complicated as you want. And this is one of the objectives of creating a new geometry library from scratch. I think I said at the beginning in the description of this workshop that the secret to being an effective programmer was that we don't have to remember details because you can hide everything within the functions and the data types and use those to construct the tools you want. I think of it as constructing the Lego that allows us to build the toys that we want to play with. This approach of using lots of functions and having functions being pure is called functional programming. And I had many slides, and unfortunately, last night I deleted them all related to functional programming. Perhaps this is for a good thing. Maybe I was going to get too theoretical about it. But I will say that functional programming is about the idea that functions can be data. Functions should always return the same output based on given the same input. That may seem common sense to you, but that's not always the case in programming. Sometimes then a function will do different things depending on the time of day or other things. And the other thing that functions often do that they shouldn't do is they have side effects. So functions that don't have side effects and that always return the same thing given the same input are called pure functions. And that's one of the hallmarks of functional programming. And another one, which we'll talk about later, is the fact that your data types don't change. Now, that's me talking. I thought it was kind of interesting to see that the same ideas resonated with the designers of the Unix operating system. And Unix is not a trivial piece of software. This is probably the most complicated piece of software you could write is an operating system. And their philosophy was do one thing well, make each program do one thing well. And if you need new things, don't complicate the existing thing, add a new thing on top of it. Now, they were talking about programs doing that, small programs, because an operating system is built up of smaller programs that work together in chains. We're applying this philosophy to geometry processing. Small functions, and if each function does one thing and it does it well, it's very robust, it's well tested, it's reusable. Reuse, that's the second part. Assume that the program output is going to be another program's input. This allowed them to come up with the idea of filters. A filter in the Unix terminology is a program whose output can be consumed by another program as input. So you can chain them together as little black boxes all doing things together. And that chain of things is more powerful than the sum of the parts. The other philosophy they had, and this predates test-driven design by years and years and years, is to try your code often and early. Try it and don't be afraid to throw away. If something's not good enough, go back, revisit it. Don't be afraid to rebuild it. That's how we get better. If you keep trying to build on top of a lousy foundation, it eventually will crumble. That applies to buildings, it applies to software. Now, the thing is that in software, most things you're building it for the first time. And in fact, you're probably the first person to ever do it. Well, who knows? Maybe you are, maybe you aren't. But assuming you have no manual on how to do it. So you have to be not afraid to make mistakes and then go back and start again. You can't overplan because it's hard to predict everything. So again, trying code, trying to do things, testing them, and make them early. So the approach we're using is to use many small functions. They should be easy to understand, relatively speaking, and they're more likely to be reusable. As a concrete example, here's some C# code. This is the type of thing you see pretty typical all over the place. ChatGPT will suggest this type of code, everyone writes it. And this is, for me, what is wrong with coding today, especially 3D coding. I'm gonna make all of my text on the side really small. So does anybody have some suggestions on what could be improved here? I'm gonna
break it into smaller methods.
Yeah, I agree with that. So why not do this? So this is the problem with 3D math programming. Everybody writes this garbage and copies and pastes it everywhere else. It's really fragile. First off, they're assuming a random epsilon, which is not great, and they're hard coding this magic number in. You know, and you always have to check it. You have to remind yourself, oh, is this how we figure out if vectors are parallel? I mean, I don't know how many people can remember that forward dot product, the upward, you know, and unfortunately, if you are here to learn how to compute whether or not things are parallel or two vectors are parallel, this is the wrong place to do it. This class is only 3 hours minus 20 minutes long. And I can't remember all of these rules. And you know what? Somebody else already figured it out. Well, what you can do and what I can do is write a function that says vector 3 is parallel forward, then this is what we can do. You notice I don't even need comments anymore at this point. The code itself is its own comment. It almost feels too sparse sometimes, but you know what? It works. It's reliable. Once you know that this parallel works, then it works. This one is, what if somebody chooses a different epsilon or got the you know, greater than in the wrong direction? Any questions? I cannot see the chat at this moment. I don't know how to make it larger, but if anyone has a question, I think you're going to have to go off mute and just yell at me. All right, let's move on. So similarly, we're talking about functions. What about data structures? You know, a lot of people don't think about this, but we have functions that are passing around an axis and an angle. So quaternion here is a way of representing rotation. And I've been battling with myself, wondering if I should really wrap a quaternion in rotate in a what do you call it, in a class called rotation. But the rotation literally would just contain a quaternion. So let's just all agree quaternions mean rotation. And we all agree, we understand that. Okay, good. What this is a static function. And I'm not giving you the details of how it works, but it's a static function. This is, well, from an axis angle, an axis and an angle, return the quaternion structure that does that. But why not just bundle your axis and your angle together and pass it around? Now, does that seem like a trivial change? I think arguably for some people, this would be like, well, why bother creating a brand new data type just to represent an axis angle? Well, the advantages of that are now you can have an implicit cast. And that's something we do in Plato geometry. Axis angle can be implicitly cast. So whenever a quaternion is requested, I can actually pass an axis angle. And it just goes, floomp, I'll just generate the quaternion magically. The other advantage is that functions can return it. If you want to return an axis and an angle separately, well, you have to do either bundle them together as a tuple, or you have to use out parameters in C#. And neither of them is very elegant. But effectively, an axis angle is a tuple of an axis and an angle. A tuple meaning a tuple is basically a collection of data types together without any particular named class. It's an unnamed class. The other thing is there's less documentations required. I wrote this little image of a camel, and the point of the camel is that little small complexities, and they add up, and they make everyone's code unmaintainable and tough because they haven't bothered to create any abstractions. So those little changes make a difference in your code base. So why is code reduction good? So code reduction means using smaller functions. It means using reusable functions, it means using smaller data types. There's less possibility of mistake if you've got less code. There's fewer tests to write. And generally, it's easier to understand, debug, and maintain and modify. So one of the things I joked about in my previous job, and it confused my manager, is I said, well, you know, I'm responsible for deleting code. If I'm able to delete a lot of code in your code base and achieve the same or if not more functionality, then I'm doing a good job. So this is another idea that you got to embrace, and it's part of the Unix philosophy. It's continuous refactoring. You're responsible for continuously improving your code. Is there a simpler way to do this? Is there a function that would make this easier to read or write? And this is part of the problem-solving technique as well. Programming is not only expressing solutions to problems, it is also solving these problems. It is starting with like a problem statement going, I don't know what I'm doing. I don't know how I'm going to break this down. So you can say, is there a function that I could use or a data type that would make the problem easier? Or would it make the solution that I'm providing easier to understand? Another thing you got to ask, are you repeating yourself? And one of the cardinal sins of programming is repeating yourself. That's why programming languages were invented. So you don't have to repeat yourself. You can use abstractions. You can use for loops. You can use functions. You can use classes, data types, whatever. Are there too many parameters? Is it getting to be spaghetti? And like I said, data structures that make it easier to work with. So programming principles we'll leave you with, and this is the end of the software engineering section, is make it as easy to understand as possible, and then even simpler. You're always coding for people, not for computers, and you're coding for yourself and everyone else around you. You better, when you come back to your code like 6 months later, it's as if somebody else wrote it. Always describe the problem in your code. And I'm not talking about in comments, but also in terms of the terminology you use and in the way you construct your code. It should be constructed in terms of the problem domain, not the solution. Nobody cares about how you solve the problem. That's not really that interesting. What they want to know is what problem are you solving? And then they'll look at your solution and they say, is it? Then they can evaluate your code and they can go, well, can it be improved? Does it make sense? One of their challenges is what you always think is obvious tends not to beat other people. They are approaching problems with a different mindset. They haven't been looking at the problem as long as you have usually. So whatever you think is obvious tends not to be. So you're always going to overestimate the simplicity of something, if that makes sense. or underestimate its complexity, whatever. All right. So I'm going to dive into some C# now. A lot of you have a Python programming background. And so I'm going to give you some of the characteristics of C# and show you some, kind of a simple program. And we're going to break it down, and we're going to start diving into some geometry. So the characteristics of C# compared to other languages, it's object-oriented, which means virtually every object, every thing, every value you talk about is either an object itself or it can be cast to an object. It's garbage collected, which means it's memory safe. So when you don't use memory anymore, it tends to be automatically released, except in some strange cases where you can create these permanent loops. But in general, memory is cleaned up for you when you no longer need it, so you don't have to explicitly free it. It's a strongly typed language, which means every runtime value has a fixed type. You can't change the type of a value at runtime. You can inspect it, but once you've created an object, it will remain its type permanently. It's also statically typed, and statically typed is different than strongly typed. Statically typed means that at compile time, I can examine the source code, I can examine the language, and I can determine that the type of every expression and variable. There is a base type, of course. You can say, well, everything's an object, and I'm going to resolve certain functions at runtime, but that is still another category. It's just that it happens to be an object. It's reflective, and that's what I'm just saying is you can actually still say, well, I can ask an object saying, well, what type are you actually at runtime? And it says, oh, well, I was instantiated as a, vector 3. Okay, great. And you can access its properties and its methods. Another characteristic of it is it compiles to bytecode, but it also compiles to native code. So some people think, oh, it's just an interpreted language. No, it is compiled into a bytecode. That bytecode is distributed, and the runtime compiles it into native code just in time, as you need it. So it's kind of like a two-stage compilation pass. But the things that you distribute are a bytecode that can be disassembled and looked at and read, which is very convenient. So the reasons I'm choosing C#, especially in the field of geometry processing, is that it's got good tooling. It's got an excellent standard library, really top notch. There's a lot of third-party libraries. It's quite easy to deploy. It's cross-platform. It's got good performance. It's got very good performance, actually. Stable. Interoperability is one of these things I just love. I can call into C++ libraries or C libraries very easily. And it's got a pretty good syntax too. I can do a lot of things very conveniently. So one of the questions, especially for the Python crowd, is like, well, what's the point of static typing? Why do I even need it? It provides a guarantee of safety at compile time, which is quite nice. So you can actually use the types system, the static typing, to find errors in your code. And that's a big advantage. And this is something we'll be talking about. You'll see how we use angle types in the Plato geometry library and how that helps us to avoid problems in terms of, angle unit mismatch and, using things the wrong way without restricting the user. It also helps the compiler produce more efficient code because it says, well, I know that this is going to be this type, so I know I can allocate the storage for it. I can do pre-computations. It also makes programs a bit more predictable. I'm not saying it's the only way to do things, but it sometimes feels to people as an inconvenience, but it turns out to be a very, very useful tool. So what is a type? A type is a category of value, like a number, a string, a vector, a mesh. And types in C# are defined using classes or structs. A value is just an entity. It's just a thing that you've created, and it doesn't change. Now, that's a bit strange because the object instance might carry data, and that data can change, but it itself doesn't change. So classes are ways of creating new data types. or collections. And the role of a class is to group data with associated operations or methods. Um, the functions that are bundled with a class are called the methods or member functions. The data elements of a class are called the fields. It also comes with properties, which are they have a syntax that looks like a field, but they can delegate to a function under the hood. So they kind of have like this, this wishy-washy kind of like, hey, sometimes I'm a function, sometimes I'm a field, or a function that calls a field, whatnot. It's fine. I just think of them as functions. Together, these are all the members of the class. So a well-designed class has a single clearly defined purpose. Does one thing, does it well. It can't be transformed into an inconsistent state. You would say, well, it should be hard, but if it simply can't be transformed into a state that's invalid, then it's well designed. It doesn't have redundant information stored. If you have extra information, like, so for example, on a vector 3, it doesn't store the normal, it computes it as needed. It can be reused without changing it. So it's reusable in different purposes. It hides its implementation details. And it also, any of the interesting work, any of the complex stuff, and the validation is all done in the constructor. So the constructor is when you say, I'm newing an object. I say new object. I want a new instance of something. I want a new vector 3. Well, that's a good point to validate that the state is correct. And that it's also when all of the related data that you need is allocated. Okay, but for an immutable class, a class that is read-only, the constructor is the only thing you really need to worry about. Because if your class is immutable, if your class instance cannot be changed, so if your vector 3 can't be changed, I can't set anything to it, then it can't go wrong. Once you've constructed it, validated it, validated it in the constructor, and you're done the creation, well, it's never going to go wrong because it just simply can't be changed. And this is a hallmark of functional programming. And this makes our lives so much easier. And I doubled down on it so much that all of the structures in Plato.geometry are immutable. You can't change them. And we'll see later that there is a way to make them look like they're mutable, look like I'm making changes to them, but I'm not really. I'm actually creating new instances and letting the garbage collector clean things up. So the role of classes at a high level is that they're an abstraction. They represent an idea or a concept, and they allow us to do things without worrying about the details. They also are for managing complexity, and that's a big part of what we're doing here, today, wherever. It's that there is complexity in this world. There's complexity in what we want to do. We need to manage it. So fewer parameters, keep fewer details to keep in the head, and related concepts, related things that you need to do are kept together. So it's 10:45. What I would like to do now is walk you through a C# program, but using Unity as the example. Unity, if you're unfamiliar with it, it's a 3D game engine, well, 3D and 2D game engine. And in it, you can write scripts while you're working on your game, while you're designing your game. You can write new scripts that change the behavior of your game, of any object within it that responds to things, that draws new things on the screen. And it's a great way for testing geometry libraries, as you'll see. Pardon me 1 second. Let me take a glass of water. So Unity, as I mentioned, it's every script is a class. And I've already described to you what classes are. Most of you already know. So it contains data. It describes what data is contained in an instance of that class and what the operations are that can be performed. So by default, if I say, hey, I'm going to make a clone script, say, well, it gives you a class and it gives you two methods on it. At the top, you'll notice that there's some using declarations. So using declarations are kind of like your imports in Python. They say, well, what library parts are being used? You have to designate the library references in your project level, but the using is it within each individual file. You have to say, well, I want to import things from this namespace. So they're used for disambiguating things. Well, I mean, for example, I've got a vector 3 and Unity's got a vector 3, and I got a quaternion and Unity's got a quaternion. So namespaces are how we disambiguate which one we're talking about at any particular time, and to make sure we don't pollute the namespace with too many things. In Unity, all scripts derive from a Unity class called monobehavior for some historical reason. And what inheritance means is that anything that a monobehavior can do, you can also do from within your clone script. So this is inheritance. I assume most of you are familiar with what that is, but you can just think of it as a way of saying, look, I'm gaining all of this additional behavior and perhaps data as well. In the case of monobehavior, scripts are added as components to objects. And so from the monobehavior, you can access other components on the same object. You can access the game object itself. You can access the transform. And there's a few other things you can do. Comments, as you can see in green, they're just for humans. They have no impact on programs. We know that. And these are the methods, or the member functions, start and update. So in Unity, it's, as you can see, there's two by default are provided for you, and there's a few others. The update is called on every frame, and start is called just before the first frame update. So the way Unity works is it's running in a big loop. So it's running constantly at hopefully 30 or 60 frames per second, and it's calling update every time. And you can actually use a setting to have it turned on, and so it's actually running also in your editor, not just your game. So here's an example of a program in Unity that's a cloner. What a cloner does is you can apply it to an object and you can get the same object repeated multiple times. So in the Unity environment here, you can see on the left, we've got the scene hierarchy, and there's a capsule object. The capsule object on the right, you can see the components. Okay, so the components, there's a transform, which is a component. It says, okay, well, this is where it is in space. You can say something which says, oh, the mesh filter, which is a holder for the geometry. A mesh renderer component, which is a holder for the information about how to draw the geometry. And this is where, graphics and geometry collide. You have a collider, which is for physics computations and for doing hit testing, saying, oh, has a bullet hit my capsule? And then we have the clone script, which we wrote. And we can see we have access to the script itself. We can double click it, opens the editor, and we've got a number of rows and a number of columns which have been exposed. And come back to the script. So all I did is write public int num rows as a field, and I initialized it with 5, same with num columns. And those were exposed in the editor here, which is a lot of fun. And I can change them. And at runtime, if my update, when each update, it will do a slightly different thing. So gold C# on the update, what it does, it's in 2 nested for loops. The first for loop goes through all the columns one by one. The next for one goes through each row. So for every column, it'll go through all of the rows. And then what it will do is it will draw a mesh, and this is a static call. And it says, all right, well, I'm going to draw the mesh that I'm associated with. So this is going through the component of the mesh filter. So coming back to the object, that is this mesh here. Get that mesh. We're going to draw it at this position. So the position is determined using vector 3. And we multiply the column by 2 for the X. We multiply the row by 2 for the Y. Notice Y up, 0. Okay, so because we're drawing, you notice that it's the X's are to the right and the Y's is up. So in Unity, it's a Y up system. Then what we're doing is we're saying there's no rotation. Quaternion.identity. That means no rotation. And then what we're going to do is we're going to use the material that we've already assigned to the object. And 0 is some other value, which I might have to do with the submesh indexing. It's not important. And the end result is this. Any questions about this code or the Unity environment that you're seeing here? Gosh, where's my chat? All right. So we're coming to 1052. Let's run through this. There's one small change here. There's something called an attribute. An attribute is information for the compiler or the host environment, and I can access it through reflection. And in this case, what it's saying is it tells the script to run the editor in the editor even when the game's not playing. So, which is really fun because it allows you to test things in the Unity editor. We mentioned what the fields were, the member variables, and how they're exposed in the inspector. So Unity is great. You can do a lot of fun things with it, and we're going to see it in action. But there are some challenges. Like why can't I just use Unity for everything? It's got its own way of doing things. Multiple math libraries, but it's designed for creating games, so it emphasizes performance, not precision. So you only have single precision versions of all of the libraries. And it's not really designed for manipulating geometry. It's just designed for rendering geometry. Usually what you would do is import geometry from another system. You can hack it, and that's what we've done to like basically do our own geometry manipulation and just render it within Unity. And we'll see an example of that. Perhaps I said I was going to go to questions at 10:55. So I have Unity running. Let's take a quick peek at it. Let's look at a little simple example and you can see what you're able to do. I'm going to open up my little arrow demo. Go and enable that. And the cool thing is you get real-time updates on the thing. So I can make it nice and long. I can change the Z up because I think that Z should be up. So I do this. Why do I say that? It's a convention that we have to choose. And you'll find that actually thinking about geometry creation is easier if you think about curves on the XY plane, on being on the ground, looking at a piece of paper, and then extruding them up. And that becomes a convention that we use in the Plato Geometry library. And there's other libraries as well that have made that choice as well. But Unity decided to go with what's called a Y-up, and Z is facing like away from the camera. So this is Unity in real time, and we can crank up the number of radial segments quite high, and it still manipulates. And of course, Unity allows us to still manipulate the transforms and whatnot. Later on, we're going to see the code for that. Actually, we can go to very briefly. Go to the code. So, there we are. This is all we needed for that code to get it to work. I hid some of the details in a new base component I called procedural mesh component, which had an abstract function that needed to be overridden. What I'm doing is I'm calling this function from my Plato geometry library and handing it the parameters, and it does all the work for us. You'll notice that within the model, there's actually a few things hidden, like there's a few extra features in my script. So hide this, let's hide that. You'll notice that there's flip winding order double-sided Z up, and it's not here. That's because it was provided here. And what it does is it says on an update, I'm going to get the triangle mesh. If I flip winding order is requested, I'll flip it. If it's double-sided, I'll make it double-sided. Oh, what does flip do? Makes it inside out. What does the die side do? Well, it confuses the world because it creates inside and outside geometry, and Unity has trouble rendering it properly because they're all on top of each other and Z fighting. And then we do have the, if it's Z up, this is the rotation that we have to provide to do the adjustment. And then we also have the little stats bar update. And what we just do is we convert it to Unity, and that calls this wonderful little class we've provided in the Plato geometry library for converting from Plato world into Unity world. So before I go, any questions, anything that in the next couple of hours you'd like to see me dive a bit more deeper into or go a little faster through? I mean, we've already covered the basics of C#, but I am more than happy to dive into some subjects a little bit. And if you tell me now, it makes it easier for me to find the right spot to insert it in. So any questions about what you're seeing, anything you want to see more of?
I have a quick question.
Yes.
Maybe I misunderstood this because I've never used Unity before, to be honest. So when in your code, when you're calling the update function, it sounds like that every frame you're kind of arraying the same object again
Yeah.
and again.
Yeah.
So is there a state in Unity, or do you kind of have to do all of your transforms every time?
It depends on what you're doing. So there's two components. There is state, there is a scene graph, and you can store stuff in the scene graph, and we can actually manipulate that scene graph on every frame and just leave it there, and it'll stay. What you saw in the code example was actually using the graphics drawing API to draw the mesh on each frame. And that turns out to be surprisingly efficient. You can still, like, Unity is very good at drawing very quickly to the buffers. So I can, from code, just as easily create a new component here. I could actually, like, just like I could in the editor, all of these things, I can go, oh, I'm going to create a new sphere, and blah, and there's a sphere. We can, like, that can be done, and it will persist. Not only, and it'll persist in the scene as long as you want it until you've deleted it. And what that does, of course, creates a game object and creates multiple things. There's actually an overhead with doing that because game objects have, a lot more extra data on them. But if I'm just want to draw something in the mesh in the scene, then using the API like draw mesh or render mesh works quite well, especially when you want to do a gazillions of objects. You can do what's called instanced drawing, and where you're only sending one mesh and a whole lot of instances up to the screen to do all of it. The disadvantage there, though, is you lose some of the more nice things, like you would lose physics simulation. Unity's got a little physics system built into it that you can use. Yeah. Does that answer your question?
Yeah, totally. Thanks so much.
All right. The design patterns use it. Okay. Okay. All right. I'm going to actually answer Ed's question before we go to break. So thank you for asking that question, Ed. When we're talking about typical C# projects, folder and file structures, I can touch on it briefly today, but unfortunately getting a bit more into it, and I agree, it's actually one of the secrets to, like, learning to use a new language. Sometimes, like, the syntax is one thing, but the tooling is what gets us. First, I'll tell you, C# tooling is quite simple once you get into it. I'll be covering it in a live presentation. So I'm doing another workshop on Thursday in New York. So I don't know if you're attending, and I'll be giving one for that. If not, I'll share with you the slides from that presentation. But I will try to bring up what I can about folders and file structures a little bit, so show you how the Plato geometry library works and how you can use it. All right, then. Thank you, everyone. I need to take 10 minutes.
Quick question,
Yes.
Christopher. Are there things that you're hoping that we have installed? Like, for instance, I do not have Unity installed presently. Should I do that over the break? Code editors, anything of that sort, or are we going to do that in time?
No, we're not going to be doing any of that for this class. I mean, if you're going to be present for the live one on Thursday, yes, there'll be an opportunity for that, and I'll share it in advance. But for this one, no. Unity takes a long time to install. It's gigabytes of data. So I'm going to walk you through it, and I'm also going to walk you through the examples, show you me coding live in front of you. But no, there's nothing that you have to install. But if you have troubles in the future, reach out to me. I owe you one for that. I'll do some custom support. All right, like I said, I'm going to take 10 minutes now, so I'll join you back at 11:12. Thanks, everyone. So what we've done is we've talked about, you know, kind of like Unity, and you're seeing some examples of what you can do with it. The thing I want you to realize is that Unity can do a lot of things, but what I'm really doing with it is I'm just using it as a host for rendering. We're using the Plato geometry libraries, which were designed to be agnostic. And I want to, you know, kind of dive into those libraries and how they're constructed, where they are, and what they look like. But to kind of understand it and get a feel for it, you need to be familiar with a couple of concepts still in C#, and we're going to dive deeper into them. And I'm not covering the whole range of C#, and it's not really syntactic, but we need to talk about interfaces, enumerables, and arrays. And to kind of like, this will help you ground you and understand some of the core decisions and some of the things that really separate the design of this library from everything else. And the cool thing is like, this is something that you can actually apply to any language. You can apply it to Python, JavaScript. Heck, I even wrote a C++ library based on the concepts. But yeah, the advantage is it's how you think about problems can sometimes really open your eyes. So I'm going to use this term, and I want to explain it. It's something you learn in computer science, but it's called an abstract data type. And what it means is it's like the idea of a kind of data that has certain operations and a certain representations. So it defines by the operations that are available. So, you know, it's usually like, practically speaking, it is actually an interface. You would contrast this with a concrete data structure, like a particular class or a particular struct, whereas an abstract data type is the idea of something. It's the idea of a stack or a list or a string. And we use interfaces to describe the abstract notion of a type. Interfaces serve a purpose. You can have a variable that is of type interface, which means it can refer to anything that happens to implement that interface. But if you think about it as an abstract data type, it's very powerful. An interface is also be thought of like a contract. It's a set of methods and properties. Oh, hold on a second. Am I sharing my screen with you all? Oh, yes, I am. Just a moment. Okay. It's like a contract. It says, well, these are the methods and properties that a particular class must implement. But it can also be a way of expressing abstract data types, because that's from the early days. That's how they were. If you learn object-oriented programming kind of the old school way, an interface is also like an abstract-based class, but don't think about it that way. That's an implementation detail. Interfaces can be used anywhere you could use a data type, as the return type of a function, the type of a parameter, a field, property, or a variable. You don't create interfaces using new. They're not instantiable. You can only create classes or you create structs. So values themselves never have a runtime type that is associated with interface. They just simply implement interfaces. So that makes sense. One of the most widely used interfaces, and is even if you've never defined an interface or thought about it, you've used one if you ever run for each through a collection in C#, because the way C# works is that any class that implements IEnumerable must have a function called getEnumerator. And for each says, hey, do you have getEnumerator? Yes, you do. Let me get an enumerator, and I'm going to call it on each iteration of the loop and see if you're done. If you're not done, I'm going to get you a value. So an enumerator, what it does is it enumerates a list. In other words, visiting each item in order one by one. So something that implements the IEnumerable interface is enumerable. It means you can visit all of the items in it. But as an abstract data type, we would call that a stream. It's a stream abstract data type. So virtually all collections support IEnumerable, but an IEnumerable itself doesn't mean that it's necessarily just a collection. It could be a file stream. It could be console, somebody typing in the console. It could be one of those gravity-powered infinite ducks that keeps drinking water. These things could all be streams of data. All right. So it's very limited. You can only get things from it one at a time. And it might not be available for a while. Neat thing about streams is they're potentially infinite. But technically with a stream, you can't go back to the beginning. And that's a bit of a problem. And the other problem with the stream is that you can't go to the nth item without visiting the first n items. The thing is that enumerables are very, very powerful. And a whole library was created around them called link. And link comes with a few basic building block functions that from there you can create tons and tons and tons of functionality. You have the select, which allows you to transform sequences of values. You have the where, which allows you to create new sequences by filtering the previous one. You have aggregate, which allows you to go through an entire sequence, one by one, accumulating the values, and zip, which allows you to combine the elements of two independent sequences to create a new one. And these can be combined together in very, very powerful ways. And one of the observations early on, which kind of motivated this, is how it was kind of like similar to SQL as a query language. What I observed with IEnumerable early on was that it only had one function, and its power was almost from the fact that it only had one function. It was a very simple concept. I can go through things one by one. I mean, I can give you an enumerator, and the enumerator itself is also, an abstract data type, and it only had three functions. Do I have a value? Get the value, move to the next thing. I'm not a fan of the move next because it's stateful. It changes the state of the internal state as opposed to creating a new thing, but that's for another day. Okay, so if you've used C#, you will hear about IEnumerable and you'll hear about link. And in the context of graphics programming, people will say, oh, you don't use that. It's not very efficient. Well, it's not very efficient because it's a stream, because you have to go through the sequence. Let's talk about arrays. Well, here, arrays are efficient. And what are they? Well, they've got counts, and you can access the elements in constant time. And some of them are mutable. You can actually change most of them are mutable. We usually think an array is mutable, which means you can set values in it. Interestingly enough, if you restrict the capabilities of array and say it can't be changed, the array can only be indexed, and you can retrieve the count, then things start to get interesting. This is another way of saying the same thing I said in the previous slide. It's an abstract data type, and the operations it provides are retrieve an element and return the count. And both of those have to be in constant time, which means the amount of time it takes to return an element has to be independent of the number of items in the list. Whether I have one item in the array or a billion items in the array, it takes the same amount of time. That's what we mean by constant time. More or less, ignoring certain other factors, okay? So that's how you describe an ADT. It's defined by what you can do with it and the performance complexity. Okay, that's computer science, basics. So here's an IArray interface, and this is fundamental throughout the whole library and everything I do. And heck, if you took nothing away, you may have fun with this because it's surprisingly powerful. So it's got two methods. Well, technically two properties actually. Remember, a property is just a method. You can implement it with a field, or you can implement it with a method. So from all intents and purposes, it's a method. So the count. Oops. Oh, come on. The count, which is how many items it has, and returns an integer, and the type of the array, whatever it is, T. So it could be an array of integers. The other property tends to be that the arrays are homogeneous. That means that each item in the array is of the same type. So in this case, we say it's a type variable T. So whatever it may be, integers, vectors, whatever, I can index it and get the element. Okay, so that by itself isn't as interesting as the fact that you can start to do interesting things behind the scenes because the interface it provides doesn't require you to set it. So you may have been taught or assumed that arrays are contiguous blocks of memories, because back in the battle days of C programming, there was no such thing as an array. It was just blocks of memory. And it's like, you can treat the blocks of memory as if it was an array, and you just index it, duck, 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 duck. And the other thing is that you had to allocate a block of memory, and you have to, you chunk it. And this is surprisingly not the case. You can actually do what's called a lazy evaluation, which means that you can compute the values when they're requested because it's behind the abstraction of an interface. So here's an implementation of Ara that is used. This is like a simplification, but it is effectively how it works behind the scenes in Plato.geometry. It says that I have what this is called a auto-backed property count, because here's the constructor here, public array in count. I give it a count and I give it a function. That's interesting. And I'll store the count that was passed in my count property. So you can set these get only properties, you can set them in the constructor. And then I copy the mapping function into this mapping variable, which is of type function. And whenever I ask for a value, that's what this means. Whenever I use the indexing operator, the square brackets, I'm going to call that function and get whatever it returns to me. What this means is that this array is implemented in terms of a function. This is functional programming. It says, I don't care how you do it. Any function that does the mapping of an integer to a value is going to work. This is like the real power of interfaces, is that I can implement them using these functional paradigms behind the scenes, and you never have to think about it. So why is all of this relevant? Well, as I was saying before, like the link operations, we know we can combine these building block link operations like take and skip and where and filter and slice and subarray and whatever. Well, they take a long time in link, but with operators, with the array operations, they're very, very fast. And all built up in terms of other ones. Let's take a moment to look at a little bit of code, just because, you know, after seeing all this theory and whatnot, it can be a little heavy. So let's navigate to this solution here. And this solution, this is, I hope it's big enough that people can see it on their screen. For sure, I can make my text here bigger, but not smaller, but not this here. What we're looking at is called the Ara3d solution. This is an open source repo. It is available.
Excuse me.
Yes. Fire.
Yeah, we're looking at the slides still.
Oh, you are? Oh, okay. Thank you very much. Let me do a new share. I'm going to stop my share. I pressed the wrong button. Screen. How about now? Yeah, you can see it. I'm showing you Visual Studio. Correct?
Yep.
All right. So
Yep.
Visual Studio, we've got my favorite windows, my Test Explorer window, Code Editor, and my Solution Explorer. Ara3d is a big honking open source project with 108 projects in it. And I'm going to show you where it is in the real world. I'm using an approach. I'm using a monorepo. But the monorepo has a bunch of subrepos in it, so that people who say, look, I just don't care about all the stuff you're doing, Christopher. I just want to see Plato geometry. Well, you can just go and it'll link you to a particular commit of Plato geometry that's being used in the repo, and you can go browse the code online. But the way I work is I put everything in one repo so that I can distribute and work together in a single solution. And if I need to do a refactoring, I can do it across the board, and I can do all of my releases using my various scripts. Within it is all of my libraries. And so, and I've organized some fun projects, Bowerbird DevOps, which is my scripts for building, project called Domo, Geometry Toolkit, which is my older, this is old, and all of this stuff is moving into Plato.geometry. I have C parsing that I'm doing, labs, things that I have fun with. All of this is open source. The interesting one is today is Plato geometry. And here I've got, like the C# source code for it. Now, the thing about Plato geometry we'll see in a bit is that it's partly generated. I have an older version of the array stuff, which is still relevant and still works quite well. And I'm going to show it to you so we can just see how it constructs and how the functions work without having to dive into auto-generated code, which was a little hairy. Okay, so we'd have to look into array. So the old name of the project. I've been supporting this thing for years, and it's been very successful for me. I've been using this for about this exact same interface. I've been using this for about 15 years now, and it's been terribly useful. Under the hood, it turned out I had all these different implementations of IRAs specialized for different purposes, but in the end, this one little functional array does the trick. There are other ones as well you want. The interesting thing is that we can do things like, let's say I do a select function on it. What it does, and this is really, really important that you try to understand this. This is an extension function. It says any class that implements IRA is going to get this function. So any class that implements IRA for a given type T, and then you can call select, you pass it a function. That function goes from the input element of the collection T into something new. We'll figure out at compile time what it is. So T is what the collection is. U is what the transformation does. The function goes from T into U. Whatever function it is, we're going to create it. And what this does is it calls another function that does the work of mapping indices by calling F, but passing it the previous value. So we're kind of nesting functions within functions. Okay, I get this. This takes a little bit of time to wrap your head around. What we're just doing is it's creating a kind of an onion effect of wrapping functions. But the thing is that there is no change to the amount of time it took to retrieve the amount of items because it's the same. The new array has the same collection as before and whatnot. Another one that's kind of interesting would be something like take. Take's a fun one. So what take does is it returns a new array containing just the first n items. Sorry, it should be n. So what it does is it says, I've got an array. I'm going to produce the same typed array, but with fewer items. So what it does is it calls a slice function. And slice goes from 0 to n. What does slice do? All it does is select It's all built on little bits that are each of themselves small and working. All right, it's fine. We're going to back away from this. All you need to know is that link operations like select and where and whatnot are available on IRA. And they're much more efficient because we're using the properties of arrays. It's built on arrays all the way up. Okay.
Question for you.
Yes, sir.
So when you say efficient, are you meaning like what do you mean by efficient? Are we talking speed? Are we talking like cores? What are we talking by efficiency?
Well, there's 3 different ways that it's efficient. It's really funny. That was a deleted slide that I had. I wish I could see them, my peoples. All right. One is that you can parallelize the operation because nothing's changed under the hood. So accessing elements can be done very quickly. The arrays never change. So they're easily parallelizable. That's advantageous. 2, functions that operate only on that are only generating values can be done without allocating memory in advance. So let's say, for example, I have the use case of saying, well, I need an index array for my vertices in my mesh. And maybe what happens is I've listed my vertices in triangle order already. And so my indices are literally 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. traditional programming, geometry programming, you have to allocate a buffer of memory. And using Ara, you don't have to. You can simply say, well, I'm going to have a range generator, and the function says given an I, I'll return an I. So you don't have the allocation. So you save there. The other is certain computations don't even have to be performed unless they're requested. So for example, if I have a triangle generator, so let's say I'm building from an array of triangles. Well, if I only ever look at certain triangles, then only those triangles will be requested, and only the functions will be evaluated for those triangles. You're not evaluating everything in advance. So you have these three kind of levels of savings. Now, is it more efficient in all cases? Definitely not. There are a ton of cases where simply allocating a buffer array and accessing it is going to be faster. So there is some trade-off to be aware of. Does that answer your question? No? Okay.
Yep. Thank you.
Yeah, it's my pleasure. Yeah, I mean, I have to be careful about making any kind of bold claims because there's always like, it depends on the context. But it's a great technique to have up your sleeve, and it's surprisingly effective at geometry computation. We used it in a kind of a real-time geometry modification system for 3ds Max called MCG, and it surprised me at how efficient it was overall in the grand scheme of things. So let's move on to the next thing. Sorry, I've got this. Okay, so this is kind of relevant because you may see this and encounter this in the documentation. Plato.geometry was written in Plato. But that's okay because I'm generating C# code from it. Plato is like the way of describing a number of key algorithms, but more also for describing the data types. I'll show you what I'm talking about here. In the Plato project, the Plato source code is actually here. So if we were to look at meshes.plato is kind of a nice place to start. You say, well, I've got concepts which are like interfaces and probably going to be changed into the word interface to avoid confusion. And then I've got types, which are basically classes or structs. We don't care. It's the same thing. Plato doesn't distinguish between structs and classes or records. Just says, it's a type. So this is what Plato looks like. Plato allows us to write the types like this, write the interfaces like that. And it's pretty bare bones, but that's great because it allows us to generate all of the extra things we want in our target language. So even though Plato.geometry is written mostly in Plato, the library itself is released as C#. And what I'm doing, when you go in and dig in the code, you're going to say, well, Chris, you've got all of this other stuff. And this is great because I've got, let's say a good example would be vector3d here. Most of the algorithms of vector3d are already written in Plato, but for the ones I didn't, I'm using the fact that C# allows you to define classes in multiple files. It's got a feature called partial. So I can have some of my vector3d implementation here, and the rest of it, let's say the dot product, is hidden in this big ass file. Oops, I shouldn't say that. But yeah, so this file, it's a generated file, which was generated by the Plato compiler. And it's got a lot of stuff in it. And you generally don't want to look at it because it's the same thing kind of repeated over and over again. I mean, why not look at it though? It is triangle 3D. It's got actually the concepts have been mapped into interfaces. Here are the fields. It's actually a read-only struct, which is great. It's good for performance. The properties are defined as fields. Again, that's for performance reasons. I mentioned earlier that it looks like a mutable object because you can write something like, I could write a function, public, let's just do void my test. And I'm going to write some code here just to demonstrate how you can change or do the appearance of changing available. For try equals new triangle 3D vector 3D dot unit X. Okay, so forth, so forth, so forth. The problem thing I wanted to point out was I can, after the fact, write try dot with a vector 3D dot unit Y, and it gives me a new try, but I have to write try equals, and it creates a new try. So the point is that the with functions allow me to do what looks a little bit like I'm changing the value A, but I'm not really. I'm just creating a new version that has the A updated. Look, so you see how it works? This is how it works under the hood. All of this is auto-generated. What else is generated? We've got a default value. We've got a new constructor. It's not technically the C# constructor. It's just a function called new, which is more convenient for auto completion. It's got some implicit casts to value tuples. It's got a deconstruction operator equals get hash code toString. These are kind of like the regular, the usual suspects when you're writing a class. You often want to write those, and Plato just generates all of that for us automatically. All right. The point is, you're not generally going to be looking at that. What you really want to look at is, how is that code used? How does somebody like write extensions to it? Now, unfortunately for you as a consumer of the library, unless you take the code and hack it yourself, which you're free to do, normally what you're going to do is you're going to import the library, and you can't use a partial, you can't define new things partially, but you can write extension functions. If you remember what an extension function looked like, it looks like this. So it's like, oh, I forgot to write a repeat function. So repeat, what it does is given any value, an account, it actually creates an array that's pointed. And this is an example of efficiency. This function can create, I could create 1 billion integers, just fill the array with 3s. But what it does is, behind the scenes is actually just calls 3 over and over again, just returns 3. So it doesn't actually allocate any array memory. But these are extension methods, and extension methods are static methods defined on a static class, and the first parameter uses this, and then you can use it as if it existed. I could actually write, first dot repeat 24. You see, and it's IntelliSense provides it a new array. So I have like the first vector has been repeated 24 times. Okay, this works for geometry too, by the way. So I could actually go, var mesh equals, and then I could write this. In theory, var xs equals mesh dot repeat 24. Well, that's very powerful. That starts getting interesting, right? Because now we're saying, well, I've got my mesh, and what I'm doing is I'm going to repeat it, to 1 million times. What gets more interesting is when I actually start transforming it. In Plato, actually, we call the select a map function because it's more common in functional programming, and select was a weird choice. We could actually say x, x dot transform, and I could actually give it a matrix, matrix 4x4 dot, create rotation or create a scale matrix, and I could scale each one, and I could actually scale each one by an amount. The list goes on and on and on. Okay, backing up. Talking a lot about arrays. I'm showing some procedural geometry. Plato. I'm going to move along here. So I want to talk about the problem. Every library or every technology one invents should exist to solve a problem in theory. And yes, there was indeed one. None is like I spent a lot of time and effort learning API after API after API. I started with 3ds Max, I think was the first one I learned. Then I learned Maya, then Motion Builder, then Revit, and Unity. And the problem is that every API has limitations. So, and you build libraries on top of those, on top of the to compensate for the limitations. I've written, utility libraries for multiple 3D packages over the years, and they also have conventions. and which is tough because the library that you build on top of that one library is stuck with the conventions that has, or the conventions of this other one. And then you're usually tied to a specific platform. You might be a particular runtime of .NET, or an operating system, or even a proprietary license like Unity. So these are all problems that exist with virtually every C# solution out there for geometry. The other problem is that C# is terrible at numerical code. Now, they're attempting to improve this lately, but honestly, it's a dog's breakfast. The more recent features in C# aren't really helping things much. And if you're writing Revit plugins that have to be compatible with 2023, you can't just use the latest, C# 13 whatever version. Either way, numerical types are really hard to write and to do it efficiently. And you have to write a lot of boilerplate. So virtually everyone arrives at the same solution, which is, use code generation. I'm going to take a minute to show you something here, because there's a very mature 3D math library that I helped develop called vim.math3d. And it has grown in popularity. It's got 111 stars. And it is tested. It's really well tested in production. We've used it a lot. It's very efficient. Source code isn't like all written from the ground up. I mean, it's open source, and it uses open source code like System Numerics and Monogame, and use these libraries. And it tried to fix some of the broken, like I mentioned, that Microsoft didn't actually even follow its own guidelines when designing System Numerics, but System Numerics is very limited in scope. But we took it, we had a Monogame, heck, we had other libraries we found as well. It's pretty big, and but you'll notice that, there's a lot of the stuff that we've got in Plato Geometry, and sometimes there's a double precision version of things, and sometimes there's not. And that kind of, at one point, gave us trouble, because, there's a quaternion, but there is no double precision quaternion. And single precision is great for high performance games and small coordinate systems up to like maybe 1 kilometer by 1 kilometer. But once you start going to infrastructure scale, it really falls apart, and you get all sorts of weird jittery artifacts. Single precision is it's a really bad box to tie yourself in, and that means like using float instead of double, vector 3 instead of some kind of vector 3 double. The other thing about this library, and as great as it is it used a text templating system, a code generation system called TT, T4. The files are TTs, and it's very powerful, and allows you to kind of say, oh, well, I've got a vector, and this is going to generate the boilerplate code for it, and it's going to generate the boilerplate code for interval type structs, and for vector type structs. And the problem is that there's a lot of custom code here, and this calls this calls template helpers, which is TT is actually kind of like a C# mixed with C# code that's executed to create more code, kind of like PHP or whatever. But anyway, this is basically how everyone's going to write their numerical libraries nowadays, unless you're doing it in C++. But the thing is that that's only one language, and it's still a bit clunky. Can't really analyzing. Then realize that Plato is effectively a fancy code generator. This Plato language you saw is generating a whole bunch of code through, there's a Plato compiler, analyzer, and then a C# code writer. Like if you go to the project settings and you go look in my thing, you go, oh, well, this is interesting. If you actually, you don't run this, because I basically run, I'm the one doing it on my side. You could, if you went in to said, oh, well, I actually care about, I want to go take a look at Plato. What the heck, where did it disappear to? Oh, must be in labs. 1 second. I'm sorry, that's very, very odd. My Plato library's all disappeared on me. Well, there's a, I'm sorry. Plato is generating, give me a second here. Plato is generating C# code from the source files using a project called Plato C#. Anyway, that's neither here nor there. What you need to know is Plato is effectively a fancy code generator. Everyone's using them. Why not make one that's actually a programming language? So what it does is it generates the boilerplate that I was showing you before. It generates a constructor, it generates hash codes, generates a toString function, implicit casts to and from tuples, which are like basically parentheses, value, comma, value, comma, value. The with X updaters that I showed you, a default value, equals, not equals. It generates all of this. Plus, it will also inject algorithms written for an interface into the class itself. And that actually saves an enormous amount of code. So we've looked under the hood. Let's talk about some geometry. The whole point of all of that effort was to get to things like this, which are high-level geometric representations of data. But I simply didn't want to go through the effort for the millionth time of writing these things and having them fragile and having to write by hand a ton of code that is kind of generally applicable. Because, for example, all of these things all have points to them. They all can be transformed by a matrix. They, almost all of them can be transformed into triangle meshes. There's a lot of operations you can do on these things, which are kind of universal. And the problem is the existing languages made it very hard for me to do that. So anyway, these things exist. And what I'm doing today is I'm in the process of basically testing everything in C# first and then porting to Plato. So the way Plato works is it's like, well, I'll just write in C#, validate that all works, using Unity usually to actually validate my results visually. I'll give you an example. I'll give you a small example just to show you that this is not just like, let's kill this sphere here, but I'm going to show you something fun. I've got this one called the All Shapes demo. And let's open her up. And we've got a few babies over here. These are not all of the shapes possible, but these are the ones that I've been testing recently and been working with. And I got a nice little ring with them. So we've got some extruded, prisms. And you may notice something rather interesting here. It's like, why is there some missing faces? Well, the way Unity works is it culls faces that aren't visible to the camera. It culls the back faces, there's back face culling, if that makes sense to you. Only shows stuff that are visible to cameras. You see, the stuff is there, it's just not visible. Well, we can fix that by trying to go double-sided, and then we get that weird. I can also see, this is probably the easier way to see it. So it's one side, I flip the winding order, then you can see the back sides of things. And this is my test case. And all of these are written, using the Plato geometry libraries. All right, coming back to it. These are the core classes that you'll find. Let's go through this stuff. So triangle meshes are like the most common types of meshes, and it's what most people send to a GPU to render, because most shaders are designed around, most shader pipelines. Sorry, it's a pipeline because you have multiple shaders working together. Most of them are designed around triangle meshes. So, and that's just the way the industry settled. You could do things differently, but it's fine. The triangle mesh minimally only needs two things. And this is the concept of interfaces being minimal. It's the concept of types being minimal. Triangle meshes, they have points, they have indices. And it just says, I don't care. I don't care how the points are implemented as long as it's an I array. Now, it could be backed by memory, but maybe it's not. Same with the indices. And the advantage of this is that, well, maybe my points happen to be already triangles, and I've just repeated every vertex, three, in a row of 3. So, and then I have a trivial indices. So this is the most basic stuff, but there are other classes which are also more useful in certain contexts. Triangle mesh is kind of like the last thing you want to get to before you send it to, like, let's say to Unity. I convert triangle meshes into Unity. But I like working with quad meshes, and I'll talk about why in a little bit. But a quad mesh basically says, well, every face has 4 points, and it's a little easier to work with. Similarly, it's also got points, it's got indices. The only thing that's different is that because it's an I-quad mesh, we know that the primitive size is 4, which means 4 points per index. So when it goes through the indices to give you primitives, which are quad 3Ds, when it gives you primitives, it knows to do that. And anybody that implements I-quad mesh gets the primitives for free. All right. We also have something called a quad grid. A quad grid is a specific kind of quad mesh that's arranged in a grid, which means that it's got a fixed number of columns, x's, and a fixed number of rows. So and then it's a grid. And we say it's closed X or it's closed Y, which says, are we intending it for it to be looped around or not? And we'll have a visual of that later, so you can see how that affects things. But 2D, that stores the number of columns, the number of rows. And if you're working with a grid, life's even better than just working with a quad mesh because you have a certain predictability about things. It's easier to navigate. So these are fun for construction purposes, and they're useful for manipulation. We also have polylines. Polylines by themselves are kind of funny. Polygonal chains, bunch of points, and they're all connected. And maybe the last point is connected to the first, which is the close thing. The challenge with a polyline is that it's actually hard to render unless you've got a special rendering pipeline for drawing lines, because lines have, 0 width. So then you have this problem saying, well, how do I render 0 width? How do I project it onto the screen and whatnot? It's a surprisingly non-trivial problem to render. But polylines, nonetheless, are actually very useful because they can be used to construct 3D shapes. You can, you can align things to them. You can loft things, sweep shapes along them, and whatnot. We also have the point array, which is kind of like, it says, hey, I just got a bunch of points. I don't know if it's connected or not, but here's some points, and that could be useful for other things because they can be useful for alignment purposes, or I can have 2 sets of point arrays and say, well, I want to connect them or whatnot, and you can use that to construct surfaces. I'm at 5 to 12, and after that, we're going to get into transforms because we're going to learn how you can apply transforms to point arrays and point lists and polygons in order to start generating some of those shapes that you saw earlier. So 5 to 12, I want to take another 10-minute break. But first, let's stop, take a breath. Any questions for me? And anything you would really like to see covered in the third hour? This is your opportunity, folks. I'm here for you.
So I guess, one of the things I'm facing is trying to deal with Revit geometry, and I want to figure out how I can, display that maybe independent of Revit. Is that something that you could see Plato.geometry being useful for?
Indeed. One of the, I'm not sure where you're at with that problem, but within Revit, you do have a tessellation algorithm, and you can request all the triangles you want from it, and that could be fed easily into the Plato. Give me a second. Plato.geometry library. Let me share my screen with you to show that there is something there. It's not just smoke. I use it, so I'm using it to. Ironically, I'm actually using it to write into Revit right now using the direct context APIs. The neat thing is that when you have a sufficiently sophisticated library, you don't have to do much in terms of the conversion layer. And it's great when you kind of like leave the world of Revit and go, okay, phew, I can go into this library and I can just work. And it's not just my library. It could be whatever library you've built on top of it, but now you're kind of free of the restrictions of that. So assumedly, whatever library you use, you're going to have your own libraries on top of it. Let's just quickly take a look. I'm going to share my screen. Let's look at the code. You can see that I'm in the process of generating various wrappers. So I actually have a Plato Geometry Revit, and I have something called Revit converters. And it allows me to go from the world of Revit, where you talk about X, Y, Zs, into the world of, Plato. So you go from, this gives me a function called toPlato on Revit X, Y, Zs. Just give me that. Similarly, I can go from a vector 3D in Plato world and generate that. Let's see what I've got filled up. Not a lot is here today, but triangle meshes are simply, they're kind of universal. Like in Revit, if I said, well, triangulate that, it's going to give me an array of integers, an array of X, Y, Zs. And then from there, I can generate a mesh. And what you would want to do next is say, oh, well, how do I generate a triangle mesh? Well, just take a look at some of the code, especially here, extensions. And you go, okay, well, how is he making tri-meshes? Sorry, triangle mesh. Oh, it goes from a quad mesh to a triangle mesh. That's cute. What about, oh, there you go, triangle mesh. To create a new one, you just need a list of vertices and a list of indices. So if you can create an array, vertices, right, you can do it. The other thing that you need to do usually going from, different environments is you need to worry about materials as well. That tends to be a little bit more tricky. Just so you know, so we talked about Revit, but I'm looking into Speckle. I've got a Speckle workshop coming up, and how do I convert? I do more sophisticated mesh computation there. So I do my triangle meshes. So I go from like that's a Speckle mesh into a Plato mesh. And I think I can go backwards as well. Similarly, of course, I've got my Unity helpers and adapters. Point was, it's not too big of a task. It is totally doable, and it's really advantageous because Plato Geometry is actually, I'm really, really proud of this, it's Net Standard 2.0, which means it is like the most widely used profile of .NET. It is compatible with .NET 4.7 framework. It's compatible with .NET 8, it's .NET Core 3, whatever .NET you are, or whatever version of Unity, it works with it. So that's a great thing about having this ground up, and it has no dependencies. And this is a little bit what is kind of bonkers. Like Plato Geometry is built from the ground up, not relying on a darn thing. All right, a couple more questions I see in the chat. Is there a detail for the Plato Geometry? How can I integrate it into Revit and Rhino workflows? Yeah, so Rhino is on my to-do list, and I would love to. First off, I'm not an expert in Rhino, and I totally need basically a motivator to do it. If somebody comes along though at the hackathon and goes, hey Chris, I got a really cool Rhino project, I'd like to use your Plato Geometry library, we can do that because I'll be at the hackathon next Saturday, so we can do it. And detailed documentation for Plato Geometry, it really is the Plato sources right now. Documentation, unfortunately, still a work in progress. So a lot of it is like, how am I using it here? Like, how am I using it with WPF? How am I using it with Speckle? That really helps a lot. Great. So those are my answers to the questions. It's 12:01. I'm going to take a throat break for 10 minutes. Allow everyone to go to the bathroom.
Real quick, if I might.
Yes.
Just one thing, like swimming in all of the information, great information. Hoping maybe in this next hour to see a few more like personal examples of ways in which you've leveraged it in order to overcome obstacles, if you have a few of those, because I'm lost in the words a little bit.
I hear you, and thanks for the feedback. I appreciate that. So yeah, okay. I'm going to keep that in mind, and we'll use that to guide like what are the specific things I've been using it for. I got a couple of good concrete examples, and I'm glad you're reminding me of that.
Awesome. Thank you so much.
Come back to ground level. It's like, yeah,
Well, I'm trying to think of how can I regurgitate this to someone else? Like what is the purpose? And it's like I've got a lot of information and I can stream it all together. But if I'm talking to a regular designer, looking for one concrete example of all of that.
Okay, perfect, perfect. Great advice. Thank you. All right, I'll see you all back here. It is at 12, 12:12. All right. Thanks a lot. Bye. All right, welcome back, everybody. Thanks for the feedback. You know, I thought it was Wade, right, who was saying about, or was it Ed, who was talked about floating and all of the information.
Yeah, that was me, Wade.
All right, yes, yes. So let's dive into that a bit first, because I have some other material and it's like, all right, I can talk about transforms and I'll talk about mesh construction and whatnot, but you know, boots on the ground kind of problems. The whole point of this is for me to not have to ever worry about another API ever again. Like I do a lot of 3D programming and I don't want to try to recall on my Unity, is it ZUb left-handed, right-handed, is it Revit, is it whatever convention it is. I just want to write something once and for all and be able to reuse it across the different things and look like an amazing programmer because I'm just using the one library as opposed to 10. And one example of that actually was quite recently. I wanted to write, I needed a PLY importer. And PLY files are, they're a very common old school 3D format. They're funny because they're very easy to write, really hard to parse. Like if you parse a PLY file, it's like, oh, 9 times out of 10, it just like fails because they're like, well, they didn't know the conventions, but I can write them, because it's very flexible. OBJ is similar, but it's actually a little bit more, surprisingly, it's more rigid. So you get more stuff, but PLY has got cute because it's got the vertex colors and whatnot. So I was like, I want to bring that in and I want to use it for testing different tools because I was writing an IFC library to speckle converter. So the thing about it is like I have to take IFC. I'm using the IFC geometry creation library written by That Open Company. Specifically, Tom Van Diglen wrote the original one. It's a C++ library that's been converted to WASM, runs on the browser, and That Open Company promotes it and has been developing it and adding features to it. So what I've done is I wrapped it in C#. And we're moving the data from that library into Speckle. So we have all these conversion labs. Now, what's interesting is I have a viewer in the middle because I need to test all of this stuff. If you're going to do transitions of geometry from A to B, you want a viewer in the middle. Otherwise, you have no clue what you're doing. You're just going in the blind. Like, how am I going to validate that the geometry is in fact sane? So I had to write a WPF viewer. Okay. That's getting bonkers. And this is exactly the path that I had to go on when I was back at Autodesk, like many years ago in a past life. And everyone was like, whoa, it's taking you a really long time to finish your job. I'm like, well, I need a math library and I need a geometry library and I need a viewer. And I was like, once I was done, it was robust. It was awesome, but it took me a long time to get there. And then I have to redo it all again. So imagine that scenario, right? I got this IFC loader. Let's take a look at it because this is practical and it is actually something that is part of the Plato today. It integrates with the Plato geometry library, and I've got an adapter for it, and it can be used. All right, so we're going to talk about a concrete problem that I'm solving. Oh, I have to make sure I share my screen. Share screen. All right, so. And this is kind of interesting when we're talking about looking at how projects work and the structures. At the root of a C# project is actually a solution. And a solution says, I got one or more projects in it, and you can organize it by folders and whatnot, because it's really powerful to think about your unit as being, a project, and having projects actually follow the same philosophy that I was talking about for Unix. A project, either it's a class library or an executable, it should do one thing and do it well. And if you need more stuff, build a separate thing that maybe consumes it. So I have this layered approach to my projects, which is why I have 108 of them. But the advantages is that sometimes I get to a point that they're actually pretty stable. I don't need to change them anymore, and they're pretty reliable. So let's look at this case. I've got my speckle. No, we'll start with the IFC reader. So I got my IFC reader, and it takes an IFC file, converts it to an IScene, which is actually in my Plato geometry library. So Plato geometry has actually got some extra stuff, which I'm not talking about today, but I have a scene library. A scene library, or a scene, it basically represents the graph of all of the objects in a scene, and some of them might be triangular mesh, some of them might be quad meshes, some might be lines, whatever, and they might have relationships to each other. So you can imagine a graph of objects. That's a 3D scene. It's a separate concern from literally just geometry. I was debating, well, is a scene really part of geometry? Should I really put it here? Maybe, maybe not. I realized you can't do anything non-trivial with just one mesh. Like, you really need scenes. And a scene is it's a tree of nodes. Nodes have objects. Objects might be line objects, they might be mesh objects, and all objects have materials. That's simple representations, but it's quite powerful, and it actually encompasses a lot of things. And you'll see this repeated over and over again in every 3D library you've ever come across. It'll have something that resembles this. All right, that's in Plato geometry. Now back to IFC converters. We've got this thing called an IFC file. Where did that come from? Well, that came from another project. All right, so I just clicked on it and it opened up a file, and God knows where it is. I use this button here on the right and it syncs me to the project. And it says, oh, you're in a project called IFC Loader. IFC Loader is an open source project which uses this little DLL. Web IFC DLL, we wrote that, I wrote that for Speckle, and it's open source. And what it does is it wraps the C++ library, and all of that is actually here. This is all code by that open company, MPL licensed, wonderful stuff. All I did was write a project wrapper around it, write a little CPP, export some functions, and what they do is they allow me to open an IFC file in order to extract the geometry, because that's the hardest part of IFC parsing, is actually the geometry extraction, and doing that in a reasonable amount of time. So I had to use that library to get out the geometry, but I just get out buffers. I get out like a mesh, and what's the mesh? The mesh is simply, given a mesh, I can get the vertices and I can get the indices. How many vertices are there? Get a pointer to them. This is C++ code, but you can actually call it from C#. And that's what we do here. We have an IFC loader that wraps it. Now it's all done in here. Sorry. What this is like the layer between the C++ code written, the DLL, that's contained in a DLL. So I compile DLL. And what we're doing is wrapping all of those little exposed API calls from the DLL into functions that I can call from C#. They've got a name, and then we use, like, C# has something called an int pointer, which kind of maps to pointers, and you can use that to do, pointer arithmetic and all sorts of fun things. Then what I do next is we put that in a file, file path, and if we want the geometry, well, we'll load the geometry data. That goes here, and now we're called into the web IFC DLL, initialize the API, load the model, and then we can actually make, once we've got the model loaded, then you can make geometry queries like, go IFC model. You can say, well, how many geometries were there? And let's get one. And if you look at the geometry, all right, all of this is just regular old fancy C#, the C# interop. Where does Plato.geometry come into play in all of this? Once you've got, like I say, most of meshes and a lot of geometry is going to be passed around as an array of vertices, an array of integers, and each library is going to have a slightly different convention. This one is pretty standard, double precision vertices in an array, and you can actually see that here. Hold a second. this is kind of interesting. If we go into here, you can see, well, the vertices are arranged this way. This is how it arranged its vertex data. A double precision, X position, Y position, Z position, and a double precision, X normal, Y normal, Z normal. So remember I told you that vertices in graphics APIs, they're going to have positions, points in space, and then they're going to have a normal, and different normals on a triangle, different vertices on the triangle can have different normals, and they're interpolated. You don't need that much precision for your normals, but it's there, it's convenient, let's just grab it. And that's what we do. Now, what does Speckle want? And what does WPF want? And what does everybody else want? Well, Plato geometry acts as kind of like a universal representation that I can convert it into and then bring it into everybody. So that's what I do here. I've got my little IFC converters. I create a Plato triangle mesh. And the key thing is I create a buffer. I do a little maps to get the vectors, get an index buffer. And now I've got my triangle mesh. Just simply, you know, an array of points, an array of indices, and then it maps really nicely to whatever else I want. So I've moved into this really generic Plato.geometry representation. And then I can now go into my WPF library. And then I can convert it into something that can be rendered in WPF. And I don't want to show you the WPF loader today because there's no way it works. I was doing too much work for this this workshop presentation, so I broke everything. But we got the WPF viewer, and then I also had the speckle converter, so I can now convert it into a speckle format. And speckle is a little funny because its mesh representation is quite different. And it assumes polygonal meshes, which is like it uses four indices at a time. Like, so the first index is how many points are there in my polygon? All right, I say, well, it better be 3. Otherwise, luckily there's a triangulate method which forces it to be triangles. But if you get a polygon, you could be like, well, the next 5 indices are the pentagon. And I have a whole section that I'm not going to get to on why polygonal meshes are a bad idea if you want to do any geometry processing, and why quads are kind of the best. So okay, let's step back. I showed you that I'm using Plato.geometry as the intermediary between all of these different APIs, but it's not like a file format, and it's not a cloud object API. It's simply a library that allows me to go, all right, I can do stuff with this now, and it's got the most let's say flexible and powerful API that I'm aware of for geometry manipulation in C#. So that's why you might want to use it. Now, somebody mentioned in the chat they would love to see a Rhino version of this. And I'm like, yeah, me too. But I'm a one-person company. Hopefully I can get enough contracts to hire a second person to help me with the conversion, or there's going to be somebody who comes along and goes, oh man, I'm writing a Rhino wrapper for this because it looks easy and it'll be super useful. And we could totally do that at a hackathon. That's not like that's only a few hours of work with the right person who's familiar with the API. And I'd be willing to support that, of course, because it'd be awesome. All of this is open source. So there's that. The other thing that I did is, like, if you look in Plato geometry, I've been expanding it and expanding it and expanding it because now I'm like, I have nothing to, like, any investment I put into it pays off in dividends, because now I actually have a PLY exporter for anything. I'll show you what I mean. IO, I've got a PLY exporter, I've got an OBJ exporter, and now of course they work for any format that I can convert into. So these algorithms just work in Revit, they just work in in Speckle, with IFC. I can convert an IFC to PLY. I can convert a PLY, well, not into IFC, but that's another story, but I could convert it into Speckle. The long range vision is this, like, Speckle's like your ability to go into any other piece of software, but I'm like, I can go into any other library while on the same computer. So there we have it. Some things that are being put into here, and I'm not sure if there's anything else to show you in there with colors and forms and shapes and primitives and scenes. All right. We're at 12:30. No, I'm going to have to move on to something kind of quickly because it's quite important, I think. And that's to kind of talk about one of the things that we would expect from procedural geometry. It's like, well, how do you create geometry from scratch? And what are the things we have to be aware of? And how can we do it, programmatically? And how does this library help you at all with that? And right now where we're at is we're still doing things that you're like, well, I can do that in Revit, or I can do that in Rhino. But I guarantee you can't do it in Unity. And also any other tool that you do it in has its own weird way of doing it. And it's completely opaque. It's behind a library that you can't release to other people and you can't use in different systems. So if you build an extrusion algorithm in this with this library, that'll serve you forever. And it won't just serve you in one context. It won't just break. So and the other advantage too is that I believe you're going to get pretty darn good performance in the long run with this guy, because I'm continuously working on improving it. So let's come into the topics that are important to cover. Just got to mention this stuff. This is really important to anybody doing 3D programming. You got to be aware of the conventions that are used. So Plato geometry is a right-handed Z-up coordinate system, and it has counterclockwise winding orders and normals. What does that mean? There's two types of coordinate systems. There's left-handed coordinates, there's right-handed coordinates. And if you look at if you do this with your hands, you're going to look silly. I can't see you. I can't see anybody's camera right now. This allows you to kind of figure out how things work. So let's say on the right, on the left, that's unity with the Y up, X to the left, and Z that way. And actually, technically, you have to turn a little bit. So your middle finger's pointing towards the screen, your Y is up, and that's a left-handed coordinate system. X is increasing, Y is increasing, Z is increasing that way. Now, other systems like Plato and a lot of others, Z up, so take that move like that, and X is here and X is Y there. Now imagine I'm looking down at my piece of paper or my table. All right, so Z is pointing up. I cannot tell you how much time is spent wasted trying to figure out this and how it affects your geometry and why your normals are flipped sometimes and not others, geometry creation. And that was like one of the trickiest parts. Also too is what I'm very happy to, like, once I solve it, I can finally forget about it and not have to worry about it anymore. And it has a lot to do with getting familiar with it, with conventions. So I always imagine I'm looking at a sheet of grid paper, X to the right, Y is up. The other thing to consider is the winding order, and winding order determines what is the front of a triangle. Remember how Unity is like hiding the backs of triangles on you? It's a performance optimization. Knowing what's front and back sometimes doesn't matter because you can just draw them both, but often it does matter, and it matters in different ways, and it will bite you if you don't know what's going on. So 1 second, I just have to cough. So you have two options for deciding the winding order, and the winding order means, like, if I have a clockwise winding order, that means I'll move my fingers, like if you can see it, I'll move my fingers like that, and the normal faces me. And that means I can see. So a clockwise winding order is with my left hand. And this is different from the other thing that we saw, actually, because you can have a left-handed coordinate system and a counterclockwise. It's complicated. But if you have a clockwise winding order for your normals, that means that I have to number my vertices in a specific order in order to see the normal, like to see the face, to see the triangle. And other systems use counterclockwise. And I like to think about it is that if I have a grid of paper and I'm looking down at it, I start at the origin with my lower left-hand corner and I start counting. And I have to number my points from 0 is the left, the next one will be 1, and then I go up 2 and then back. So I draw, you can't see this, but I'm drawing a little line. Just imagine you're looking at paper, you draw to the right first, you draw up, and you draw back, and that's my winding order. And it's the same for my quads. So my square, it starts there and everything has to be done with that consideration in order for me to get all of my geometry to appear correctly and have the correct winding order. So this is really important, and it doesn't matter what the convention is. Any API, you have to think about this stuff, and this is where we all screw up the first few years, and all of our so many mistakes are based on that. And the fact that certain transforms, like if I do a rotation around the x-axis 90 degrees, it suddenly changes my winding order. These problems all happened. Okay. Plato's got numbers and integers. We've got our own angle types. I told you that's wonderful because I can now say 0.5 turns. I can say 180 dot degrees. I can math that by radians. They're all angles. This is something to remember. Angles having their own type means I can't screw them up anymore, because I don't know how many times in Unity where they show to users, well, here's a value. It's representing, sometimes it represents rotation, 0 to 1. Sometimes it represents degrees, 0 to 360. And all of the math libraries in the world want radians for whatever reason, which hurts my brain. But now I wrote all my libraries to use angles. I don't think about it anymore. It's it accepts an angle. The cool thing is that angles auto, cast. Like I can cast it, give it a number, and it'll say, well, fine, I'll assume it's radians because you're too lazy to tell me. But you can have full safety if you want. Cool thing is I can write functions that accept angles, and it becomes a lot easier to validate them. Not as important. We have transforms that we could talk about. We can talk about it at length. I'm not going to talking about it in length. I'm going to talk about it quickly. Converts points technically. It converts points from one coordinate system into another. The way I think about it is you can move, rotate, or scale points. We could call translate. You'll hear the term TRS, transform, translate, rotate, scale. The reason why is that the order in which you perform your transformations matters. If I translate, then rotate is different than rotating and then translating. Think about it. If I move an object and then rotate, it's going to look like that. If I rotate an object and then move it along the x-axis. But here, think about that. What happened was when I did the rotation, now it's on a new coordinate system. It's on a rotated coordinate system. My mouse now sees x this way. I see x this way. It sees x this way. Technically like that, but you know what I'm saying. Coordinate systems are relative. They're always relative to a frame of reference. So that's kind of what we mean by coordinate system. We don't mean going from transforms don't necessarily mean going from barycentric coordinates to spherical or to polar, whatever. There's other coordinate systems as well. And we don't need to get into that. This was just to show off that there's math behind all of this, and there's matrices. What do you need to know about matrices? They represent, well, 4x4 matrices can represent a 3D transformation in space. And the most common ones are translation, rotation, scale, or some combination of. They could be multiplied together, and the multiplication, the result actually represents the transformations done in order, which is kind of cool. But the order matters, like I said. The order of multiplication matters. 3 times 4 is the same as 4 times 3, but a matrix 1 times matrix 2 is not the same as matrix 2 times matrix 1. Go figure. Multiplication depends on the types of the variables. We use 4x4 matrices often for 3D transformations, but it's not always easy or useful. One thing to note, matrix times a vector is a transformation. But we have 2 types of transformations to consider. One is the transformation for points, and the other is the one transformation for vectors. And why are they different? Vectors are not affected by translation. And if you're talking about normal vectors are called normal because they're all supposed to be normalized. They're supposed to actually have a length of 1. You don't want to scale them because that would screw up your results, and you don't want to rotate. You don't want to, move them. They just rotate. They just point in a different direction. There's just some like common transformations, translation, rotation, and scale, but there's others as well: shear, reflection, projection. Projection matrices are interesting. They allow you to go from like 3D onto a single plane that represents the camera. So you can have perspective and orthographic projections, all done as transforms represented as matrices. This graphic, which you may find useful, is the fact that it shows in how affine transformations. It's just a type of transformation. It works in 2D as well as 3D. It's actually easier to understand in 2D a little bit. And you can see how these different types of transformations have different types of representations as matrices. And here's the end results. Why is all of this relevant? Well, let's move along. Talked about meshes. We need to talk about the construction of meshes from curves. Let's see. I'm going to dive into this example, creating a capped prism, because what we do to create a capped prism is kind of interesting. All right, prism is basic, isn't it? Well, I'm not sure how I could say this. I don't want to give it away, and I kind of want to make people engage. Does somebody want to explain to me how they would construct a capped prism, like just algorithmically, just saying, oh, well, somebody says I want an 8-sided prism that's capped. How would you do that, algorithmically speaking? And does somebody want to venture an attempt at that? This is a big thing. No wrong answers, by the way. No, nobody's biting. So what, and like, I mean, just maybe you're just talking from the point of view of a tool, like a tool they should use. I'm actually honestly curious, because I don't know, like, I don't even know how to do this in tools. My whole dream is to become completely like able to code anything you can do in a tool by hand using C#. That's my dream, so that I don't actually have to learn how to use the various tools. And the one I learned first was 3ds Max. All right, so I'll give you a hint. Well, let's look at it first. Actually, we'll look at it in action, and then I'll explain it to you, and then I'll show you the code. And I think that'll be a nice way to kind of finish up this workshop. All right, let's go into this demo. I'm gonna turn off the old shapes. Turn off the old demo. There's something called a polygon demo, which is cute. Where are you? Polygon demo. All right, here's a shape. All right, let's just. So let's pull it down a notch. That's kind of interesting. We have a 5-sided figure. That's a pyramid. A prism. We have a 5-sided prism. So a prism is a polygon that's been extruded up, right? And we could change the height. Let's make it a capped one. Well, it's hollow underneath. Remember, you can see through back faces, but here we go. It all works. Here's a fun algorithm. Oh, we can do something called star skip. So we're actually connecting every second point. That's cute if we do things like 7. You can, and then we can of course make it a pyramid. You get an interesting shape. All right. So how did we do that? Well, I extruded a shape and then I capped it. Let's look at that in code. There is an extension method called toCappedPrism. It takes an array of points and the amount you want to extrude. Then what it does is it creates a prism. Then it gets the top points. Now, what's this saying? Skip. It says, I want you to only look, I don't want you to look at the first n points. I want you to skip over the first n points and give me the rest. because now what we're saying is that the prism has twice as many points as it previously did, right? Because an extrusion goes up. I see a chat. I'm very happy about this. Shift the index extrusion. Yeah. Yeah. Effectively, that's it. Well, what's kind of interesting though is actually how prism is made, and this is where Procedural Geometry does some neat things that makes life easier for all of us, and it'll be kind of our little cherry on the sundae, so to speak, because we are starting with a shape with two sets of points. So what I'm trying to say is, look at prism. It has an array of points and an extrusion amount. So what do? You call the extrude function. Well, what does the extrude function do? Well, what he does is he needs a does a sweep. Sweep is a generalization of extrude. This is kind of interesting. Extrusion is a special case of the sweep function. Sweep says, well, I have a function that says how I'm going to transform every point in my original to a new one. And what I'll do is I'll apply that function to every point. So I deform my original polyline into a new one. Remember, this is one of the advantages of immutable programming. I never hurt the original thing. The original thing is always the original thing. It's always there. All I'm doing is creating a new one. So deformations, in this sense, do not change anything. They create something else that is a deformed version of it. If I need the old thing, it's still there. So what this code here is saying is I'm creating a quad strip. Look at the quad strip. This is funny. You have to go down and then back up to understand this. Trust me. So quad strip says I got an array of points on the bottom, and I have an array of points on the top, and it might be closed, it might not be. What I want to do is make a two-dimensional array and then convert it to a quad grid. Well, that's kind of interesting. If I have a two-dimensional array of points, remember what a quad grid looks like? It's a grid of points, and it might be closed on one side and it might be closed on the other. And this allows us to express a ton of interesting shapes. So using a quad strip, or I can generate a quad grid, and using a quad grid, I can convert it to a triangle mesh. In fact, quad grids convert to triangle meshes automatically. You just return it. And so, for example, I have this combine function, which isn't listed here, but what he does is he takes two triangle meshes and gives me a new triangle mesh, which says, I got some point, I got a mesh here, I got a mesh here. I'm just going to make a new mesh that's just got, the two things side by side. So the cap plus the extruded points. It's cute. So what we did, we had created a prism, we get the top points, we create a fan from it, which is basically, you're appending a certain point in the middle, compute the fan indices. So fans are just like basically, well, I mean, they're a simplification of a pyramid. A pyramid is like a fan, but the center is up. But if you do the fan, you can do it all the points in the middle. And there you go. That's your cap. And let's just look at quad strips and quad grids again in a more meaningful way so that they actually make sense for all of us here. All right. So we can finish on a really nice thing. Let's talk about this torus here. There's some fancy math to describe a torus, but it's surprisingly simple, actually. We go, there's an X, a Y, and a Z, and A's and C's are constants, and the varying parts are the U's and V's. Okay, it's a parametric equation. Let's see if I can express this another way. Here, Revit explains this as it calls them faces. And it says in the Revit API, it says that there's two input parameters, a U and a V, and given a U and a V, I can figure out any point in space. And I can do that for a number of different types of things. I can do it for a cylinder. I can do it for other things. I can do it for a torus. So the torus parametric equation says, given a vector 2, or a UV, 2 numbers, I'll give you 3 numbers. I'll tell you where on the surface I am using those UV coordinates. Well, if you think about it, every time you do that, if you have the UV coordinates, you can create grids very nicely. So if I have the torus function, look at this torus function. Isn't it beautiful? That was it in math. Here is it in my library. It looks pretty much the same. The angle, number. U dot cos, v dot cos, sine, whatever. It's an equation. You write it down, you forget it. I mean, that's the glory of it. And we know it's a torus function. And by the way, I got my UVs as in a vector 2, and I got it in the range of 0 to 1, which meant 0 to 1 turns. So once you figure that out, it's kind of interesting. So you literally say uv.x.turns, uv.y.turns. So I pass it. This function is the parameterization function, which calls this one, which is the way it wants to be written. So this is the way the mathematician writes it at the bottom. This is the way the programmer writes it. And this is the way you use it to generate your grid. So you say, I can generate a quad grid using a function that takes vector 2's and then whatever I want. This could be any lambda I want in the middle here. And then as a resolution, it says true. Okay, let's look at it. Let's look at it in action. So this would be it's called a quad grid demo because it's the generalization of quad grid. Double click it, go to it. All right, here we are. Here's my cute little, like, wow, Chris, it's just like it was in the screenshot. Why is it only part of a torus? This is why. And let's look at something here. I'm going to turn all of that off. I want you to see this. All right, cute. This is a torus with a little bit missing at the top and a little bit at the bottom. There's a quad grid creation function, which says all I need to create a quad grid is, a quad grid is the function that maps from UV coordinates to 3D coordinates. That's called a parameterized surface. All right, and then I'll draw it for you. Let's go see that function that does the quad grid drawing. Use here. Let's go like there'll be an extensions 2. Long story. So there it is. There's my quad grid right here. To quad grid, give me a function mapping from 2D vectors to 3D vectors. Give me a grid size that you want. Tell me if it's closed on the X and closed on the Y. Why would you even so it makes sense for a torus to be closed, right? That makes sense. But there's other shapes possible. What if I swap out for a different function? I want to, let's say, a plane. Well, closed, this looks good, but if I say, and it's empty in the back, okay, that's a normal plane. If I say it's closed on the U and closed on the V, what happened? I got some weird artifact going on. Well, what's going on? Oh, he's drawing it on the back as well. He's all confused. So what happened was he's looping around and trying to draw it on both sides. And then you're having some kind of weird errors. All right, it's fine. I'm saying is that not all 2D to 3D functions should be closed. But in the case of the torus, we want it to be. So let's go back to our torus. And let's close it. There's another thing we could have done instead. I have an option which I was kind of experimenting with. It's kind of fun. It's called inclusive U and inclusive Y. What if instead of actually closing it, I just generate points? Do you see the difference between, okay, look at this. Now, look at that. There's a slight difference in the shading. The shading here is continuous because the normals are interpolated correctly. And if I do it this way, the normals aren't. What inclusive V and inclusive Y means is that I'm parameterizing in the range of 0 to 1, as opposed to 0 to just before 1, and then connecting the last point. That's the difference here. So it's cute. You have 2 ways of creating geometry from quad meshes. But but I mean, just it generalizes from a single function that's been sampled over a range. And that range here is expressed like, okay, I'm going to only do it 0.5. So I'm only going to have half a torus, and I'm going to do this one 0.5. Well, I'm only going to have like a quarter of a torus, but it's that quarter. Maybe I want to have more. Maybe I want to have more here. And maybe I just want to start it at a different place. I can do this, change the starting point. Okay, all of this is doing is playing with this cute little function here. This is surprisingly simple code. And that's why this makes me so happy, because it was a lot of work, a lot of words to get us to a point where the quad demo is that simple. Choose your function. So that's the function. That's the new function we got. You're going from a vector 2 to a vector 3. Well, it's either a disk, a sphere, a cylinder, or a torus. Everything else is the same, and we can express different shapes. So let's look at those different shapes. Sphere, disk. It's a cute one. So folks, we're coming up fast to 1 o'clock. I'm kind of pleased to be able to show you all of this. The one thing I remember first seeing somebody doing geometry programming and functional programming at the same time, it kind of blew me away. I said, wait, there seems to be something missing here. They're cheating somehow. And it comes down to the power of A, using mathematics, and B, using functions as data, and saying, look, rather than me saying everything on how to do it, I'll just give you the formula, and you apply this formula, and you do it. You do the work. And that's the functional programming nature, is saying, like, well, this is the thing I want you to do, and it's expressed using this function. Just apply it and do your work. So passing functions is one of the biggest ways you have of saving time and energy. So with that, I want to open up for some questions, thoughts for what I can do next time. You know, I'm going to be at I'm going to New York next week, so I'll be around at the hackathon. I have another class on learning and programming, so if you have some questions about basic C#, I hope you show up for that, and you can definitely give me feedback also for that class. So that's it. I'm going to stop sharing. Make sure I can see everybody. Folks, your turn. Time. You're probably tired and hungry by now.
So do you think it's like, because you showed us how to build this from scratch, but would it make more sense for us to just like maybe build onto what you've done instead of trying to build our own thing? Like is that kind of the goal with this GitHub, I guess?
Yeah, it'll be on NuGet probably by next week
Okay.
as a package you can download. So I'm in the process of like transitioning a lot of other packages I made, and I had made a very big investment in another library, and I just like, now it wasn't the right way to do it, so I went this kind of hard route. So as a NuGet package, what that means for people who don't know, it means it's a package you can easily download into an existing C# project, whatever it may be. Probably even consume it from a Revit plugin or a Rhino plugin very easily without too much muss and fuss. You just say, well, go to package manager, go on NuGet and say, search for Ara3d and you'll find, or sorry, Plato.geometry, and you'll find it. Now, the way I recommend using it, yeah, you use it, look at the source code. If any function doesn't quite work for you, write your own function, and you can just cut and paste the code. I know some people like to consume the entire repo, and I don't recommend that. Don't take the source code. It's just, it undergoes a lot of churn, and you won't be able to pick up new improvements as they come along. Keep in touch with me. I mean, this is an open source project too. I want to see it used, and I am going to be using this myself to build, well, I'm already building a 3D viewing tool based on WPF, but I'm building another one that's going to be a commercial grade 3D editor. And this is all going to be open source, and it's going to power it. And I've invested a lot of time and money into making that happen. So this is not going away. I don't think this is going away at all. And even if somebody like bought me out, they'd be like, "Oh, it's stuck with that open source repo." It was something that a fellow I knew from Mesh Mixer, a guy named Ryan Schmidt, he did the same thing. He's like, "Oh, you know what? I put all my shit on GitHub, so that if I got bought out by Autodesk, which happened, they couldn't take it away." So yeah, hopefully you build on it. Yeah. I mean, the challenge will be, of course, the community adoption. I understand like lack of documentation, and it's like, oh, these are some new ways of programming, and without a ton of examples out there and a ton of tutorials, it can be hard. But you know, I'm a determined fellow, and I'm out there to make it happen. Also, the other thing I'll mention, if your company goes, we see you're doing this, and you're like, it's saving me time. Well, you know, you can always reach a contracting agreement of sorts, like small. But I'm just saying, it's not going away.
Do you think that, you know, you mentioned documentation stuff, is that maybe a good place we could start helping out, just so we could learn the library and help document things?
Interesting point. See, we haven't, it's an interesting thing to talk about, actually, because nowadays I saw an amazing hackathon demo for AECtech in Barcelona. This group, they used an LLM to generate all of their docs. So it's really fascinating. Part of it, though, too, is like to design the docs. How do you design it in a way that it is easily consumed? Because a lot of that stuff can be automated. I'm generating a lot of code, analyzing a lot of code. So yeah, I think the docs is something to collaborate on. It's just not old school, literally sitting there writing stuff in the same ways that we used to. We need to leverage, you know, tools for analysis, LLMs for doing that. Yeah.
Yeah, it makes a lot of sense. I guess my last question then is there, you know, because performance, I think, is a big conversation when it comes to geometry, right? What do you think you could do to further enhance performance, or, you know, how do different languages impact performance? How does the implementation impact performance, I guess, too, is probably a big point of it.
Let me think about that for a second. So languages don't really impact performance that much. It's largely about how little you touch the data. So a quick performance lesson. Don't touch the data very much. For really performance intensive stuff, I mean, you're going to leave it in the arrays that they come in, and you do the manipulations as little as possible. So, but yeah, C# is like, I think I can beat everybody in terms of performance. I've worked on a lot of performance intensive operations, and it's crazy fast. The one thing that kills me is the fact that C# compiler is not as fast as it should be for dealing with certain types of code. So when you have like lambdas within lambdas, it goes, oh, well, I don't know how to optimize that. And it does these long chains of calls. But that's going to go away. See, the investment here is the fact that by building all the libraries in Plato, I can actually run a static analyzer on the code and go, I can inline that, I can inline that, I can inline that, I can inline that. As code gets written in Plato, more and more code can get optimized, and then I just output the optimized versions to the different targets. The question really is like, you don't understand how slow and how bad existing libraries really are. Like, they're really crummy. Like, our computers have gotten so fast, and I'm sorry, like the performance I see out of Rhino and Revit and everything, even 3ds Max, it's all garbage. So yeah, it's not that hard to beat. The other thing is do work on the GPU, like your instancing, like instancing is a big thing. So in architecture, it is a ton of repeated instances of things, and just do the work on the GPU. Do your, you know, your culling. You do your instancing on the GPU. So good data representation is the key to all of that, and we're not even worrying about that. But the first thing you need to do is you need to have all of the foundations correct. I need to have everything working and correct before I can move on to that. I did a lot of high performance optimizations in Unity 6 months ago, and I built some libraries for it, and they were written in C# and they're crazy fast. But the problem is that I needed a really robust library that could cover all of the bases and that could be fully tested. So testing, documentation, once correct, then we're going to go for speed, and we're going to beat everybody.
Sounds good to me.
All right, everyone's starting to head off. I really appreciated being a part of this workshop, and the audience has been great. I really appreciate the feedback, the level of engagement has been awesome. So I hope to see you folks, some of you, at the symposium in person next week.
Yeah, thanks so much for a great presentation. Also, if I can sneak one question and just out of
Please
curiosity.
do. I got a couple more minutes.
So Plato looks very powerful for like low-level geometry operations and like generating geometry.
Yeah.
How high level does it go? Like, can you do like Boolean operations, or like where is the ceiling there right now?
It's really fascinating. I did an experiment the other day with Boolean operations. So one of the advantages of Plato is that it's actually designed as a functional language. So it's got knowledge of, you know, higher order functions and whatnot. Boolean operations tend to be done on triangle meshes. And my philosophy was that you could actually have better success with parametric representations of your shapes. So if you know, like, oh, I got a parametric. See, we didn't get into parametric definitions. So what I did is I was showing you quad meshes, right? And I said, oh, you go to a quad mesh and then you go to a triangle mesh. But what I actually do is I go to volumes and I go to surfaces and I go to parametric surfaces first, and I leave it in the numerical representation much longer. And then you can do the Boolean operations on the numerical representations. So you say, well, I mean, like a torus is not a quad mesh. A torus is a continuous surface, right? So mathematically speaking, it is literally one function plus maybe a transform applied to it. So you can do some really interesting stuff if you work with it at that very high level. And the performance has been was astounding, actually. We were doing Boolean operations in real time in Unity with that type of representation. So it was validating that. But as I said, I have to back away from the performance. Like I get carried away with it. So to answer your question, it's a specialized language that's specialized for numerical stuff and mathematical stuff, but with the higher order ideas of functions in it. And yeah, sky's the limit, I think, with higher order stuff like that. Where I want to play. So the space I want to play in is actually more sophisticated and organic designs and shapes. I want to kind of go into where sneak into where Grasshopper is playing a lot. So it's part of the hope from here. It'll be really interesting to see where this works. If we do this type of workshop again next year, where we are with it and having different tools rather than having to, you know, tack on top of Unity. I'm hoping like my own editors and stuff will be able to be available.
Cool. Thank you.
Thanks a lot.